Hello everyone, I warmly welcome you all. My name is Tomasz Pirowski. Many of you may know me from my courses where I teach you how to write a multimap for switching, secure our programs, link them to the vehicle identification number, utilize Ghidra, and incorporate our code into the software. So in this course, however, I would like to teach you how to modify diesel engines appropriately. While many such courses are available, it's essential to debunk some myths, clarify misconceptions, and explain precisely how the ECU functions. This knowledge will help you feel confident in our modifications and allow you to predict how the car engine operates accurately. So, our work will be conducted using WinOLS software. I've used this software for over 25 years since I began my career as a car tuner, working with VTEC Tuning and VTEC Dyno, my companies, and also for Volkswagen Racing and Kia Racing as a software engineer. So, while alternative options are available that may offer similar editing capabilities, I would prefer to focus on WinOLS. I noticed that people who ask me about Stage X recent entry into the market, but we focus on WinOLS. Before we move on to the example I prepared for our educational session, I assume you already have a basic understanding of using WinOLS. However, if I mention any hacks, interesting tricks, or ideas, I will provide additional explanation as needed, assuming you have a solid grasp of the fundamentals. So I use Windows version 5, and I recommend that you do the same. For our work, we will need a specific file to edit. So I have chosen a file of the BMW edition EDC17 Bosch ECU, which you can download directly from the course page. I encourage you to do so. Yeah. Left side, on this side. Yeah. Mirror in the camera. To begin, let's outline the plan of our course, where we start and where we aim to go. So we will begin by understanding the basic flow of information through each diesel ECU, regardless of whether the manufacturer is Bosch, Delphi, Siemens, now it's named Continental, or another company. So once we have developed a set of main loop maps and parameter setting maps, separate group, so will be our focus, yeah? This will be our focus, so we can proceed. Although limiters will be also considered, of course, we must consider them. We will first concentrate on preparing these main groups, documenting them and learning how to calibrate them. After that, we will move into accurately calculating the composition of the fuel mixture. This will enable our engine to achieve what we need to refer to as a stage 1. For this purpose, let's assume that the stage 1 involves 20% modification, which means an increase of 20% in torque and increase, of course, the 20% in power. So because the power is calculated as a torque multiplied by RPM and, of course, the certain factor, so thus by increasing torque by 20%, we also achieve the 20% increase in power. That's logical. So it's essential that the engines we plan to modify for the stage 1 upgrade can handle these demands and have the necessary reserves. So once we have mastered this material, we will learn how to effectively search for maps and small details like switches, specific points, SCR, AdBlue, whatever. So it is important to note that we will not be using what are commonly referred to as Damos files, which are A2L files exactly. These files are generated at the time of the ECU compilation when the manufacturer produces it. Yeah, so they document the structures within the ECU, the maps we name it. Yeah, and assist in analyzing and calibrating it, the ECU, when preparing the final version or subsequent versions of the vehicle software. So To digress for a moment, it's essential to recognize that manufacturers can produce an incredible variety of uh, program versions for a single engine. It explains why we often see multiple updates for one engine rather than one single optimal or semi-optimal update. They are testing it on humans. You buy the car, you are the tester. You paid for that, yeah? Once we learned how to search for small details, we will also understand how to transfer our knowledge and what it means to propagate the information. We will take our insights, including both characteristics and minor details, and apply them to new places, which may involve different engine control units. So these may not necessarily be from the same manufacturer, even, but could come from similar models. For example, moving from EDC17 in a BMW into an Audi, or even, let's say, Chevrolet or Infiniti. So we will generally avoid pigeonholing ourselves and limiting for our focus to just one group. We will reject this notion, aiming to show that through collaborative learning that we should not restrict ourselves. The knowledge gained in this course should apply into any car model, regardless of the manufacturer, and yield predictable results. This word predictable is very important. So, building our tuning must lead to predictable outcomes, of course, not just in terms of power and torque, but also regarding the appropriate air to fuel mixture, exhaust gas temperatures, or limitation of the back pressure. So, it's crucial to manage back pressure, for example, on a turbocharger to prevent damage, ensuring that these engines are reliable and operate under decent conditions without damaging these machines, these engines. Yeah. So it's not necessarily the case that something will break immediately, but after some mileage, there could be issues like clogging of the filter or burning components. So it, of course, it is not our goal. We aspire to be responsible tuners, confident in our knowledge and abilities. So, unlike car manufacturers and software issue developers, we don't have access to huge laboratories for testing. So, therefore, we must carefully consider the data we can log from the vehicle. Sometimes we can't capture everything we would like, and the information we do get must be sufficient to ensure that our solutions work smoothly, at least to a certain level of performance. So, as a fundamental principle, we need to recognize that all diesel engines, and indeed all engines available today, whether in cars, trucks, machinery, agriculture, or this combined machines and so on, tractors, operate on the same basis theory and system. They have even the same fuel. Although this system has undergone slight upgrades and evolution to meet the new environmental standards, it has remained effective and reliable, starting from early 90s. So, consequently, all vehicles utilize the same principle and same underlying system. There is no unique or special method for tuning for a specific engine, such as this BMW we have here. While there may be minor hacks or tricks, I believe in that, yeah, and certain limits may be, for example, set lower by the manufacturer in particular models, and they need a special adjusting. There is globally there isn't a unique approach. Mm, there is unique approach, mm, and we should just modify all the engines similar way. No reasoning behind modifying any specific engine in a specific way. This notion is a myth. The second major myth I have encountered is the belief that the vehicles cannot be modified using percentage changes. Regardless of how we approach the modifications, whether by applying fixed torque settings, adjusting the conversion table from torque to fuel delivery, or making other operational changes, the outcome will still rely on percentage changes. It is because the fundamental operation of the engine is based on proportions. So proportions are percentage. Even though there has been a recent emphasis on focusing on the air-to-fuel ratio at the forums, blah 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 blah, and the composition of the fuel mixture, it's crucial to understand that mixture composition, even the simple mixture composition, is the more important than merely what we input into the ECU or how we shape the torque limit characteristics to appear neat and artistic, round. Recognizing the significance of mixture composition is a fantastic achievement in itself, but it is a percentage. Yes, significant achievement. Understanding this, I would like to humorously emphasize that it involves maintaining an optimal air-to-fuel ratio by proportion, so by percentage. Specifically for a diesel engine, this ratio is approximately 14.6 to 1. This is a stoichiometric. This ratio can be also expressed as a percentage, so 7% or less is for fuel in the whole mass of the mixture. Therefore, there is no escaping from percentages. One must ensure that the mixture composition is correct for every operating point, every single possible condition. These percentages truly constrain us. No way. The more we ignore certain factors, the more crucial they become. Otherwise, our work may not be done accurately. We can use various online calculators from various very famous tuners to help us to input individual maps and tables to and calculate something which will guide us on adjusting other tables accordingly. However, if we look closer at the formulas used in these calculators, we will quickly realize that everything is calculated based on percentages. This highlights a key point. We must either calculate the air-to-fuel ratio accurately to ensure optimal operating conditions for the engine at all times, at all places, or working points, or our results may be inaccurate. While the engine might still function, it could always operate better. So the key point to understand is that cars depend heavily on the type of fuel they use. We often assume that all cars and at fuel stations are filled with fuel of the same quality and standards. So if that were true, their designs would be quite similar. However, this isn't the case. Some manufacturers have innovative solutions that set them apart from others. Unless we we are discussing Mazda. I love Mazda, which consistently surprises us with its unique designs. When one manufacturer produces a significantly better product than its competitors, the others will likely study it, buy it, reverse engineer it, and adopt those inside once the product enters the market. No other way. That's how it works. In my practice of reverse engineering of ECU control units, ECUs, I use Ghidra to analyze them. Formerly, I used the IDA Pro, but I still use it. I own the license, but now I use Ghidra. So this process is similar to what the manufacturers do, except we must make another assumption, that all engines are constructed similarly. The primary factor linking all engines is the fuel they utilize. Engines must be built comparably to effectively handle the fuel available at the stations, and everybody has the same chance, same fuel. Additionally, when we use WinOLS, I will tailor specific settings to meet my needs, which I will demonstrate shortly. Okay, so maybe I will remove my face from the screen so as not to distract you. My initial focus will be on adding all the loops maps. Maybe I will minimize myself. So I will name these maps specifically to make them easy to locate later when we write our explanation in a text editor. In this project, I will first set up the appropriate subdirectories. While this step is primarily for educational purposes, you won't have to do this in the future. Yeah, just to speed up your work. So I will create a directory called main loop for main maps, just a sequence of the main maps. There will be, as you would see, that there will be only 4 of them. Additionally, I want to organize the maps based on their names. Specifically, any map with a period, if I add period to the name, yeah, dot, in its name will go into that folder. So I will create a second directory for maps that specific, they set specific parameters. So any maps with underscore will be placed there. Finally, I will create a folder for limiters with no special characters in their names. They will initially go into the main loop folder, but we will later redirect these maps or rename to the limiter folder. Yeah. So for now, don't worry about how I search for these maps. What matters is that the maps follow the same sequence in ECU of the same type. While there may be multiple sequences, the number is limited. For sure, limited. With older EDC17 ECUs, there is often one universal sequence, except it was a Fiat Ducato. But all other follow the same sequence. The entire flow of the information in the ECU begins with a driver intention, driver wish, represented as a percentage of the pedal. This structure is displayed in grid format with a vertical y-axis, y-axis for some of you, and x-axis corresponding content. Data is processed based on the intersection of these axes, like that. So we can label the top with the gas pedal position to make this data more readable. The value is 100% of throttle is represented by 8192, which is equivalent to raise it to the power of 13. Yeah, if you just look for coincidences. So it is one common method of recording the 100% value. Although it's not only one, it can be 32768 or 1024 to up to 10, for example, or 32,000 and so on and so on. It is to up to 15. If we need to, we can remember these values at the top and store it in our repository of conversion factors. I've already memorized it if I wanted to add it, I will simply enter its name here. So this description field is not related to the map or axis names, which people often confuse. Instead, it pertains specifically to the area involved in the conversions by factors and offsets. So these conversions are managed through coefficients, which allow us to convert parameters linearly. Yeah. So returning to the topic, don't mind the name of the map we see here. It might seem amusing to the people. The description field is associated with these conversions, which are stored there. While this may not seem straightforward, this is how it is organized. We must follow. No other option, yeah? So, look at the x-axis. I have already completed the conversion and even indicated the percentage. I obtained the conversion factor, which I now refer to as 100%. I typed the value that this number represents, specifically 8192, and stored it in my set of conversion factors. I can show the conversion for any selected point by holding the Shift key. If I go back and select it again without holding Shift, the conversion will be applied. Well, simple, just using the table of conversions. Good to have them. I will label this characteristic as 1A, this map, which means I will go to the main loop where we write this as a driver switch. Having recalculated the x-axis, let's focus on the y-axis, y-axis, which represents RPM, revolutions. I noticed that the RPM for EDC17 drivers should be divided by 2, so we need to multiply it by 0.5. So this means divide by 2. We can write this as a 0.5 or simply .5 or comma 5, and all the notations are acceptable. In older controllers, so it was EDC16 or EDC15, just in museum cars, there is no need for conversion because it's one-to-one. However, in some other controllers, different conversions may be required. For example, you might need to multiply 0.25 in Delphi. Sometimes in other systems like Siemens, the conversion is still one-to-one. So we still need to recalculate the value of the main map, which represents the torque requested by a driver. So we select the torque map, which should be converted by the factor of 0.1, additional 1 0 of precision. So therefore, we enter .1, and that completes the conversion. So what does that mean? If the driver presses the accelerator, for example, to 50%, and the vehicle has a engine speed of 2000 rpm, then the car will implement 215 Newton meters of torque. I will place a marker here, so we can use a Ctrl plus 5 or F5, sorry, or press the marker from the menu in this way. While it may not appear very powerful, this marker, for sure, not a big thing, in a hex dump, the view of the entire file, in 2D, it looks more substantial. So if we examine this file, this view, we will also find a small marker at the bottom. This is just visible, which I hope is visible. Additionally, we can navigate quickly between such markers, moving to the previous or one or the next one. It is in menu that you have the shortcuts. So now let's return to the characteristic I was working on. Here are marked which parameter will be sent further. At the moment, if the driver presses 50% of the accelerator pedal and the vehicle speed, engine speed, is 2000 rpm, it corresponds to 215 Newton meters. You might wonder what happens if the driver presses 40% of the accelerator pedal. We do not have that value at the axis. Would there be an interpolation between these two numbers? Yeah, this is how it works. It's not the case. The values in the system are interpolated. If there is an instance where the value is not exactly defined, such as exactly 1850 revolutions or so, the interpolation will be based on 4 points within the characteristic map, within the map. It is essential to remember that the values are always interpolated within this map, and nothing occurs in discrete steps. No steps, not at all. Interpolation. When we switch to the three-dimensional view at the bottom, the controller moves smoothly along the surface rather than jumping between points. So feel free to ask questions about this or what may occur if the value of the axis is exceeded. For example, if the motor reaches 5,500 revolutions, it's over. Hypothetically, we are not breaking it. Italian can do that. Sorry, Italians, you always rev too high. Okay, so for example, if the motor reaches 5,500 revolutions, hypothetically, it won't explode immediately. However, it raises the question of what value will be realized in that case and which line the values will be derived from. And will the controller predict what happens next? No, it will not. Instead, the controller will use the last available information, particularly from the line corresponding to 5000, because the highest we have 5000. Now, let's start taking notes. Yeah, we'll start taking notes. I will just open the Notepad. So we will keep it in Notepad. I will create the new blank document labeled information flow. Initially, we have added the first map, referred to as the driver switch map, and I will label it as map 1A. Yeah, the reason for naming it map 1A will be explained shortly. Now let's record the values on the axis. So the y-axis will represent revolutions per minute, RPM. The x-axis will represent the position of the gas pedal, just proportionally. You press half, it is a 50% of the answer. And the resulting data, which is inside the map, will be required torque from the driver switch. So we will write on the x-axis revolutions and on the y-axis revolutions, and on the x-axis pedal percentage will the resulting product being in Newton meters. Yeah. The next section of this information will move to map 1B, which will represent the torque limit. The torque limit is essentially the map that could be implemented using a driver switch map itself, as the solutions exist. Sorry, my cat scratching my sitting place. Note that the maximum torque we aim to achieve in a system is set directly at the 100% position of the x-axis. So the final line, there would be no need for separate torque limit map if we properly set the final column. However, historically, the limit has been established and retained as a component of the driver system up to present day, so we must live with it. Yeah. So thus we need to treat these maps as two separate entitles of the one map while editing them, even though conceptually they function as two separate characteristics. It is one map. So this is why I designated it as a map 1A and 1B, allowing us to consider them together in our understanding that the torque limit could correspond directly to the column in a driver switch map, the last column, very last column, not the last column. So at this point, we have established the driver switch map. I will return to the hex dump, which provides a comprehensive view of the entire structure. I'm navigated through the section that addresses the AGR, excess gas temperature, excess gas recirculation. So ecological solution, yeah, up to the torque limit. So there are several limits. However, I will be adding a single primary limit. Here we have a lot of limits. So I will add a single primary limit which has only one axis and data structure. Please understand that in the future we must modify all of them, but now for basic analysis I use one map, one single map. What should we do if this map does not generate automatically? We can position ourselves near the beginning of its axis, which approaches 0, bottom line. I switch to the text mode now to locate a small positive number. Here it is, standing 21. So I right click on 21, I press the colon K, and then I press the letter K from the German word Kennfeld, so the map, resulting in a completed map. So now when we return to the hexdump view, it will display the nicely formatted map. So next I enter the map and assign the appropriate name. I double click to do that, just into the map, ensuring do not to click where the axis is, as that would lead to edit the axis properties itself. To avoid mistakes, I always click in the data area in the middle. Sometimes it can be narrow, one line for example, but still I click in the data area. Let's call this map 1B, ensuring I'm in a correct location within the main loop. I do not forget about the dot. So in the main loop, we are calculating the torque limit, which involves the multiplying by 0.1, and then the unit for torque will be Newton meters. On the x-axis, where we have rotations, this rotation should be multiplied by 0.5. Yeah, we keep the same strategy, effectively dividing by 2. Yeah, half of them. So to recap, we started with 2000 revolutions where the gas pedal is pressed at 50%. This we have agreed from our driver switch map. Since the gas pedal input is considered invalid at 2000 revolutions, we are at a specific point we will mark.